Hello everyone, my name is Arnaud Caron. I am with Korea Tech, Korea University of Technology and Education, which is located in the Republic of Korea. Today I will share some results with you about how surface oxides affect the friction and wear of metallic glasses. As we know, friction is a very usual phenomenon which in fact limits the efficiency of any mechanical system that involve moving parts. On top of it, friction ultimately leads to wear of mechanical parts and to their failure. So both friction and wear have utmost economic impact, which means it is very important to control friction and design wear-resistant materials. Usually, friction and wear can be limited or retarded by using some lubricants. One essential lubricant are obviously the oil-based lubricants with some additives. However, we need to bear in mind that oil-based lubricants have some environmental impact, and some applications require to work in dry conditions. So in that case, we could think of using solid lubricants instead, or thin film coatings. One very promising solid lubricant is graphene and other 2D materials such as maybe boron nitride or molybdenum disulfide. So graphene has attracted a lot of interest in the tribology community, and it has been found that it has indeed very good lubrication properties. However, we need to keep in mind that the lubrication effect of graphene really much depends on the orientation of the underlying substrate. So we showed recently that when there is good registry of the graphene lattice onto the lattice of the substrate, the friction coefficient of graphene is indeed very low. However, once we lose the commensurability between graphene and in that case copper, the friction coefficient increase dramatically. The reason for this is as soon as we lose registry between graphene and the copper lattices, we in fact increase the likelihood for the formation of fold and the activation of the puckering mechanism. Another promising solution to reduce friction and limit and retard wear of metallic surfaces is the development of tribal layer. So we are currently working on the formation of such tribal layers on a eutectic alloy, where we find that upon scratching on such a microstructure, we first deform the lamellar eutectic structure, in that case of a silver copper eutectic alloy, and ultimately refine the lamellar structure until we in fact may mix copper and silver together with some oxygen to form a very nanocrystalline or maybe even amorphous tribal layer. So in this work I would like to discuss another solution to limit friction and retard abrasive wear on metallic glasses by growing a surface oxide. So metallic glasses are attractive alloys because of their high strength and because of their ability to be thermoplastically near-net shaped. So metallic glasses are very hard, and from that perspective we would expect that their wear is very limited. However, the literature is not univocal about the tribological response of metallic glasses. One reason owes to the complexity of these alloys and their surfaces. So we need to keep in mind that metallic glasses are multi-component alloys with very often elements that are prone to build oxide layers, and for that reason the properties of the surface oxide may have a very large impact on the tribological performance of these alloys. So if we consider some theoretical background of friction and wear, where we may first need to consider that any engineering surface is never perfectly smooth, but that in fact the contact between two engineering surfaces will, in most of the cases, if not in any cases, initiate at some asperities. Such asperities are in the dimension of the nanometer scale, at the nanometer scale, and in fact we will see that a single asperity can be well modeled by using an IFM tip, which have similar dimensions. But before we come to discuss how to model the tribological behavior of a single asperity, I would like to remind you that according to Bowden and Tabor, there are essentially two mechanisms that lead to friction and wear. The first mechanism is the shearing of an asperity sliding onto a surface. So the shearing can be described, or the shearing force can be described as the product of a shear strength tau times a contact area between the asperity and the contour body that depends on the normal force. So here we make the assumption that the shear strength is load independent, while the contact area A follows usually either the Hertzian model for elastic contacts or its modification by considering some adhesive forces. In this case, we would rather apply the Johnson-Kendall-Roberts model. And now in the case of plowing, we consider that an asperity is pressed onto a surface at some threshold load, so that it starts penetrating inside the contour body, and upon sliding it will essentially plow inside the contour body and push some material ahead of it. In that case, the plowing force can be described as the product of a plowing coefficient times a normal force. So in any case, if we combine both contribution, we would obtain for the friction force that it is simply the sum of the shearing force and of the plowing force above a threshold value of the normal force. So if you want, the shearing may be brought in analogy with adhesive wear, while plowing is the analog to abrasive wear. So I mentioned already that we can use an AFM tip to model the behavior of such single asperities. And in fact, AFM tip provide a variety of asperities. We could consider using a single crystalline silicon tip, which those tips are very sharp, but since they are very sharp, they may break easily. Instead, we could consider a polycrystalline diamond coated tip. There we may lose a bit of sharpness, but those tips are very robust, and a compromise between two tips would be to use a single crystalline diamond tip. Note there are other types of coatings for AFM tips, such as metallic coatings, such as gold, platinum, or recently there are also platinum silicide coatings that are essentially also very hard, and those tips are usually quite sharp. In this work we used atomic force microscopy as a nanotribometer. I won't go in very much detail about the working principle of an AFM. I would just like to show you the principle of the nanotribological measurements. So essentially we sled the cantilever back and forth over a scanning area upon the application of a normal force, and the scanning was operated with a given velocity v. So upon scanning, we can both record the topography evolution, which means we can determine image after image on the same area the evolution of the roughness. And after the full sequence of measurement, we can then image the worn area in tapping mode or in non-contact, for example, in order to determine the wear volume. Parallel to the topography measurement, we also can determine the friction force on each scanned on corresponding to each scan. And now, very importantly, once we have such a friction force versus normal force plot, we can distinguish between the two mechanisms, which are again shearing and ploughing. So shearing is usually fitted in the low load regime, and we usually know where to stop, because once ploughing sets in, we first have a significant increase in the error bars in our friction signal, and also we observe a roughening of the surface. So once we have determined the shearing and fitted the low force regime with the equation I showed you previously, which is the product of the shear strength times the contact area, we can simply subtract the shearing fitting curve from our experimental values to calculate the ploughing force as a function of the normal force. And this then allows us again to fit the ploughing force with a linear curve, and the slope of this curve is then the ploughing coefficient. In the remaining of this presentation, I will present some results obtained on a nickel niobium metallic glass, which was produced by melt spinning. So we had ribbon-like samples. And we have immersed these samples for different durations in two different types of acidic solution. One was 0.5 molar solution of nitric acid, and the second one was 0.5 molar solution of hydrochloric acid. So after immersion for up to 5 hours, we washed the samples in distillated water and measured the surface topography by AFM. So what we observe is some smoothening for up to 2 hours in both types of acidic solutions, and after 5 hours of immersion, again some kind of roughening. The surface composition were then measured by XPS, and depending on the type of acidic solution, we find very different oxide formations. After immersion in hydrochloric acid, the main constituent of the surface is niobium pentoxide, with no nickel oxide contribution, while after nitric acid exposition we rather have a niobium oxide present at the surface. So before immersion in acid, we measured ribbon surface by friction force microscopy to do our friction and wear measurements, and we observed that we had a significant amount of abrasion. The shear strength deduced from this fitting was around 1 gigapascal, so that corresponds to the shear value, or the necessary stress to shear off an asperity between tip and surface. Note the tip here was a polycrystalline coated polycrystalline diamond coated tip, and after scratching we observe a significant amount of pileups that speaks for really abrasion. Now, importantly, after different duration of immersion into nitric acid, we find that the shear strength does not really change. However, the amount of plowing force, means the amount of abrasive wear or of plowing friction, significantly decreases. So that means by growing a niobium oxide on the surface of this metallic glass, we are essentially retarding abrasive wear, and so extending the regime of shearing friction. So this is also confirmed by imaging the surface after scratching on these alloys, where we find now that the amount of pileups, or the height of the pileups, is much smaller than before immersion into a glass, where we had pileups that went as high as 200 nanometer, while after immersion into acid, into nitric acid, the pileups are only in the range of up to 30-40 nanometers. Now, even more interestingly is if we now grow a niobium pentoxide, we find that we completely suppress abrasive wear. We now only have shearing friction. Now, these points here are rather outliers that correspond to the transfer of sample material onto the tip, and maybe again the discharge of this transferred material from the tip. So, and correspondingly, we also find here that the pileups after 1 hour in hydrochloric acid are rather low. We do find some increase in pileups after longer immersion into hydrochloric acid. However, it rather looks like we are smearing the oxide of the sample surface as we would smear butter onto bread. After these measurements, we then imaged the used tips on the different surfaces by scanning electron microscopy, and we indeed find that the amount of transferred material at the end of the tip increase after immersion into acid, and that the amount of transferred material is the largest after immersion in hydrochloric acid. So to finish this presentation, I would like to show you now some results obtained on zirconium, cobalt, aluminum, metallic glass. This was, or the samples were produced by casting. So here we are dealing with a bulk metallic glass. And before scratching, the sample of these samples were mechanically polished, and we measured then the topography in the as polished state, and after immersion for 8 hours in hydrochloric acidic solution with different molarities. So in one case it was 0.5 mole per liter, and in the latest it was 1 mole per liter. So again, we find, what we find is essentially no significant change here in the chemical composition of the surface, and also the topography does not significantly change. At least the roughness parameter RQ remains in the range of 2 to 3 nanometer. So we proceeded in the same way as for the previous alloy. We slid our diamond tip onto an area of 2.5 by 2.5 micrometer square, and recorded the friction force as a function of the normal force. And again, here we can fit our experimental results with the shearing model over the whole range of normal forces, and in fact we do not find a significant amount of wear on this sample. After 0.5, after immersion for 8 hours in 0.5 mole per liter hydrochloric acid, we again do not see much change on the surface. In fact, the extracted or the determined shear strengths remain the same in the range of 1 gigapascal, and again a similar result after immersion in 1 molar solution of hydrochloric acid. So with this, I would like to conclude that surface oxides retard the onset of abrasive wear and significantly decrease the friction loss. The properties of the oxides are, however, dependent on their growth conditions. So if we now compare between the effect of nitric and hydrochloric acid, we find that chlorine ions may mechanically destabilize the surface oxide, and which results in the smearing of the oxide layer upon sliding. Also, the composition of the underlying material is determinant for the properties of the surface oxide, as shown ultimately on the zirconium cobalt aluminum sample. So last, I would like to state that selective oxide growth may open a new route to control friction and to retard wear. So with this, I would like to close my presentation and thank you for your attention. Also, I would like to acknowledge the contribution of my students at Korea Tech and collaboration with Professor Zhang in his group at Zhejiang University in Hangzhou, China.